6 or 7 years, and a few years before that as a hobby. So it's a project close to our hearts. Before we start, I'd like to underscore one point. JRuby is Ruby. We're going to be talking about differences, but we have to underscore the fact that it's very important to us that we're as compatible as we can be with the various versions of MRI, because we want it to be a drop-in replacement. If you go and write a Ruby program and try running it in JRuby and you fall on a bug, you'll probably say, oh, screw JRuby, and not try it for another year, or maybe never again. So it's very important that we try to be as compatible with Ruby as we can.
Well, if any of you saw Brian's talk in the last session in here, Ruby means all of the implementations, and that's what we aim for. We want to be a Ruby language implementation that matches as much as possible what the Ruby language does. So that may mean MRI if we don't have a good specification, or it may mean the more abstract Ruby. But JRuby is Ruby just like MRI is.
We'll be honest, we're a compatibility project, and we have some holes. There's some POSIX APIs that we can't quite cover. We did start a JNR POSIX library several years back, and we've been slowly adding missing pieces, so that will continue to get better. We basically dropped native C extension support for 1.7. And mostly just because no one's really stood up to maintain it. So if you really have a strong interest in seeing this continue forward, you should come and talk to us later. But it was also kind of a confusing picture because people would go and install a native C extension for performance or speed, and we would load it. And Brian was talking about this earlier. We do actually put a lock around calls out to the native C extension because we don't want two threads trying to call into a C space that's not thread safe at the same time. And that kind of has lackluster performance.
And we have to make all the same tricks to pretend that the objects that are floating around are real pointers when they're not actually real pointers. So you end up losing a lot of the performance gain you would have gotten from going to a C extension anyway.
And then we'd see a tweet saying, JRuby's incredibly slow, wow, wow, wow. And, and the truth is there was a JRuby native equivalent that was out there that performed well. So C extensions were good for loading certain things that we wouldn't have been able to do without C extension support, but it just kind of muddled the picture a bit. There's a few things we'll never be able to do. The JVM is never going to allow us to fork. We're going to be able to support a very small portion of what callcc can do. We've also made some decisions explicitly not to follow MRI. We default object space to mostly off. So if you go and load, object space still keeps track of modules and classes, but not every object in the system. You can turn that on if you want to, but for 99% of the use cases, you have no need to.
And we'll talk a little bit later about why we made some of those sort of decisions. You'll see it. You'll see the numbers.
So JRuby is Ruby, and then some. And the rest of the talk is going to be about and then some. We should make an announcement. Last week, we finally put out JRuby 1.7.0. Woo!
It's over, I think, over a year and a half since 1.6.0.
We forked a year and a half ago. We only have two major bullets here, 1.9.3 by default and production ready, and invoke dynamic support's baked in if you run the right JVM. But a year and a half's a lot of commits, and we probably didn't backport half of them.
Yeah, thousands of changes and improvements in 1.7.
If you've never used JRuby, all you have to do is make sure you have Java installed, and you can just install it with the RVM. Simple. Try it out, use it, love it, whatever. So we're an open source project in the same mold as most open source projects. We have a group of developers that are committing to our code base, and as an open source project, we have dependencies. Well, we have a huge dependency, and it's called the JVM. But another way to look at this is we might have a contributor like Yoko committing to our code base to fix a an embedding API, but then we might have a JVM engineer like John Rose adding a new optimization to the JVM. So in a sense, we have a much broader team. If we look in contrast to MRI, there's a lot more flexibility in that they can make their own subsystems in their own runtime. But we kind of like the idea of letting other people do it for us. And what's great is by building on top of the JVM, we don't have to make our own garbage collectors. We don't have to worry about jitting to native code on all the platforms we support. There's tooling. Native threading was built from the start in Java, and that's not easy to add, and so on and so forth. I mentioned John Rose, so I thought I'd put his picture up there. He's a pretty attractive guy. He's been working on Hotspot for 15 years. A cool fact I just learned is he invented a programming language. I think it's called C star. I don't know how the star is pronounced, but he made it with Guy Steele. How cool is that? And he's also in the Invoke Dynamic lead. And Charlie will talk about Invoke Dynamic later. So we decided to have a thought experiment. What if in 2007 or 2008 we decided just we're not going to develop JRuby anymore, and we're not going to let anyone else do it. So let's see what happens.
That would be JRuby 1.0, basically.
Yeah, so at JRuby 1.03, it's about 23 seconds to go and run red-black tree with Java 1.4. Now today, it's about 3 times faster with Java 7. This is pretty stunning.
We can just sit back and basically let the JVM get faster, and JRuby keeps getting faster.
Yeah, give me another margarita. But then we thought, oh, what if 1.86 stopped developing today? Or back then at that time. And amazingly, we actually caught up to 1.86 by doing nothing. So I think this underscores the power of relying on the JVM. But let's go a little bit deeper through some of the things mentioned in the previous slide. It's cross-platform. It literally runs everywhere. Standard platforms you'd come to expect, but OpenVMS, AS400, some guy was running Ruby on Rails on AS400 talking to Microsoft's SQL server? Or was it Access?
It might have been Access.
It might have been
I'm not
Access.
Sure. Yep.
We
yep.
enable great
people do
things.
this. We enable people to do wonderful things.
It's expanded to Android. Android's done a great job of pushing Java back into the mobile space.
Who here even knows what AS400 is? Okay, that's surprising. Only at this conference would I get that many hands. Most of the time, there's just a bunch of blank stares.
Here's our open bugs for OpenVMS support.
If you want to dive in and fix some of the OpenVMS support, go for it.
Or you can just tell us how to get a copy of OpenVMS.
Yeah, we don't even know how to. We don't even know how to test this.
How
do we get access to an OpenVMS system?
I think you need a wheelbarrow full of cash to get it.
Of all the old systems that I have in my basement, there's no VAXs or anything else like that. I have no alphas. I mean, I don't know what I'm going to even run it on. So we depend on our OpenVMS users.
The second great decision of the JVM is they compiled to a neutral Java bytecode format. So you compile things once, and then you can run them in many places. So if you look at this list, these are the Java native extensions that exist right now. And you don't have to compile them when you install the gem. Now, why this is important, does any Windows users out there? It's tough. It's tough installing native C extensions on Windows.
Has anybody ever gone to production and had a C extension installation fail? A few people, yeah.
Probably more.
Or local, or any time. There's all sorts of things that can go wrong in the process of building a C extension, and these all basically just distributed as binaries and just drop into your gem directory.
There's 47,000 Java libraries. Now, a lot of you might think, oh yeah, there's 45,000 Ruby gems, but there's 45,000 Ruby gems with like pry-john2 released
Yeah.
That sort of pattern doesn't actually happen in Maven. So it's a much more impressive number than it might look.
Yes. A lot of good uses for Dix and Dix Streamer gems as well. If you haven't installed Dix, you can have a lot of fun with that. A lot of useful gems out there too.
There's a lot of languages out there. When I put this together, I kind of threw the COBOL thing as a joke, but then I realized, well, crap, there's a lot of legacy apps out there. This is a big deal. And polyglot in general is a big deal. I love writing stuff in Ruby. It's a great language. But is it the best language for absolutely everything? Of course not. So use the right tool for the job. The other great thing about the JVM running multiple languages is they run within the same VM. So you get this holistic view because language A and language B both have, they're both based on the same basic object, same garbage collector, same tools to look at the performance and how much memory is being used and so forth. And another weird side bent of polyglot is every single language likes to go and reinvent their own wheel. Well, some of those wheels are awesome, maybe more awesome than the Ruby wheel. So you just have another dimension of choices.
All right. So I'll take it to the next one, GC here. So GC does matter, and it makes a tremendous difference for the performance of an application. Anybody that runs a significant Ruby application on MRI is eventually going to see some GC issues that they have to deal with or tune it. I mean, this is basically the primary sell behind Ruby Enterprise Edition, was that the GC was tuned a little bit better, you could make your own tuning to it, and it was designed to fit a process model, forking model better. GC is a huge, huge issue for a lot of applications. And Ruby itself is very object heavy. If you've ever done any object counts of an application that's running, it's a tremendous amount, like massive numbers of strings, massive numbers of arrays all over the place. A lot of people say, oh, well, you know, it's okay, we'll just keep our processes small and have a bunch of them. Well, if you've got 10 processes all doing 10% of their time on GC, you're wasting 10 times 10 of all of the CPU time in the system. You're wasting those resources by having to split it up. I believe that any application that gets above a significant size is going to have issues with GC running on MRI. There's just no way to avoid it at this point. What we have with the JVM is a wide variety of options, ranging from small applications up to very large applications with large heaps, many cores, many threads running at the same time. It scales up extremely well. There are JVM applications out there that are running terabytes of memory, terabyte-size heaps, and having no major issues with it. And these really are the best GCs in the world. If you go back and look at GC research over the past 10 years, 90% of them are talking about how this would be implemented on the JVM or implementing it for the JVM. So it's all there and available for free if you run on top of the JRuby. Now, just on OpenJDK, which is the one that most people are going to end up touching, there's a parallel collector that uses multiple cores, stops the world, but it uses multiple cores to clean up stuff as quickly as possible and keep the pause times short. There's a concurrent collector that still stop the world parallel for a young generation, but any old objects out there, it'll collect it concurrently with the application executing, so you don't see pauses. G1 is intended to be concurrent for young and old. There's also a serial single-threaded if you just want straight throughput as fast as possible for a smaller application. There's other GCs from other VMs, like the C4 continuously concurrent collector crazy. So I don't know what the other C's are, but I mean, it's a real zero pause garbage collector that you can just drop a JRuby application into and never see a GC pause. That's the sort of thing that we've got. And Tom mentioned it briefly, but the fact that we have the homogeneity of all objects and all libraries and all languages that run alongside JRuby means that they all take advantage of the same GC. We don't have separate memory models. We don't have separate extensions that have their own way of managing memory. It all fits into the same world. And so every piece of code that you're running with a JRuby application lives in that same excellent GC. So I've got some demos and numbers here to talk a little bit about GC on the JVM versus other options. This first one is basically it's doing a lot of heavy GC with a mix of old and young objects, but the heap is steadily growing over time. So we can see what the effect of a larger heap has on GC times. This is the meat of it. So we've got a couple loops, inner loops, outer loops. Inner loops are creating young garbage that's going to be collected fairly soon, if not immediately. The next loop out is creating an older garbage, older data in memory, as basically a chain of objects. And this credit to Evan Phoenix for coming up for this, for testing young generation, old generation stuff. And so I went to run this and get some information on what the GC times and number of GC runs look like on regular MRI versus JRuby. And this is the first result that I got. And I had to go logarithmic with the vertical scale here to even have JRuby show up, because MRI was spending so much time and doing so many GC runs that it completely buried the JRuby numbers. And if we look at the amount of time being spent, I didn't have to quite go logarithmic here, but still we're talking about orders of magnitude more time spent on GC in MRI versus on the JVM with JRuby. And so then I thought, okay, well, let's look at individual GC times. JRuby 193 and higher and JRuby with 1.7 have a reporting feature that will show all of the collections, what the heap sizes were, and how long they took. And this is the sort of graph that you get. You can basically look from left to right here and say, this is the maturity of an application, or this is the amount of data an application is going to have to process, and this is the exponential increase in how much time you're going to waste on garbage collection with that same application. Well, JRuby, the JVM, it's all staying flat along the bottom. However much data you have in memory has much less effect on what GC is going to need to do. And you know, this makes people unhappy when an application that gets larger and more popular and becomes Twitter or becomes somebody else starts to have all these pauses and delays in it. And so this is also a graph of the heap size of your application versus the unhappiness of your users. And that's not a good curve there.
The eyes are off screen.
The eyes are off screen, but you can see the frowns. So, you know, so a lot of people say, okay, well, it's not so bad. We're talking about, in this previous graph, about 200 and some milliseconds for this size heap. Well, what if your heap gets larger? And so I've got 8 gig on my machine. I carried it further, and I even went to Ruby 2.0, which has a bunch of garbage collector improvements, and it continues to get worse from there. This is now counting in seconds per GC pause. If you have a gig heap, you're at about a half second, and then it continues to go up from there. So you split it up. You say, okay, well, I'm going to split it up into multiple processes. Well, you've got each of those processes doing 1/4 or 1/5 or 1/10 of the same amount of work, essentially. So, I mean, the findings when I started running through this were kind of what I expected. With JRuby, you get lower, more uniform GC times because the GC doesn't do a lot of unnecessary work. Reduced or eliminated pauses depending on which type of GC you want to run. And you can go to massive heaps with still consistent application performance, consistent GC times. Any application that gets above a certain size is basically going to need a VM that has a garbage collector like this. And JRuby is not a bad option. So the next one would be threading. Again, a thing that we mostly get for free from the JVM. There are things that we've had to do to improve Ruby threading and figure out what it means to have concurrent execution of Ruby code. But with JRuby, a Ruby thread is a JVM thread, is a native thread on pretty much every platform. So you do thread.new, you can run that on another core completely in parallel with the main thread or with other threads that you've got running in the system. So one process, one JRuby process, can actually use all the cores in the system, saturate all the cores in the system, and you don't have to spin up and manage a dozen processes to make that happen. This also means that one server instance can handle all of the requests for your site. We've got people that run applications on JRuby pushing tens of thousands of requests on eight-way systems with one process, one JRuby process that maybe is 200 meg, and that's the entire application. Much better way to run applications than having 30 instances of a process and having to manage all of them and then wasting all the resources across them. So another benchmark, this is the non-parallel version of it. It's basically just creating a big array and then walking over it a bunch of times. If we parallelize this just to see what we're actually getting as far as parallel performance using all the cores in the system, we'll just change that from 10 times going to loop to 10 threads that are going to loop individually, and then join them all and see what we've got. So, as you'd expect, with unthreaded, just the single version, the direct 10 times loop, we get one core that basically saturates, and it's using all the CPU on that one core. If we go to threaded,
it's still basically using almost exactly the same amount of CPU time because none of those threads are allowed to run in parallel. We get the same 100% of one core just sprinkled across all the cores because they are native threads, but they can't run concurrently. Now, JRuby, pretty much the same. You'll see that we've got one core that's close to being saturated. We've got other cores that are actually doing a little bit more work than in the 1.9 case. That's very likely the parallel GC running off to the side while the application does its work. And then, I mean, this is even better than a 4-core. This is actually getting the hyper-threaded cores on the machine as well, saturating an entire CPU just by spinning up a few Ruby threads. This is actually possible to do. If we look at another benchmark, there's a threaded reverse benchmark that we use with JRuby. Basically walks a bunch of strings and reverses them manually rather than using the C or Java code behind the scenes to do it. And you get a pretty good improvement every time you add threads. And we've got various reasons why it's not linear, but you can reduce the runtime of a benchmark or an application or a big data processing system by using threads in JRuby, which you just can't do right now in MRI. So you notice that it was nonlinear and it kind of tails off. Well, there's various reasons for it. One of them is that we can only get memory from the system as fast as at a certain speed. We can only garbage collect objects at a certain speed, because that's also going to be memory access. And it's a proven law that there's only so much parallelism we can get out of a given application. Depending on how much of the app you can parallelize, you're only going to be able to get up to a certain amount of increase, no matter how many cores you throw at the problem. I would love to have a 65,000 core machine, but obviously it's not going to help if I can't parallelize enough of my application anyway. Okay, tooling. This came up in Brian's talk. This has been a constant pain point for folks that work on Ruby and need to be able to monitor and manage their applications, diagnose problems, profile stuff. So we get all the stuff that the JVM has for free. We get all the profiling tools that are available. And since JRuby is just written in Java and some Ruby, your Ruby code eventually compiles down to JVM bytecode. These profilers basically do work with Ruby too. So there's lots of choices for profiling JRuby applications that are essentially just JVM tools. We also have some built-in features like -- profile, which does a basic flat profile just out of the box. Profile.graph, which will do more of a graph form. There's a HTML output, JSON output, and so on. If you pass this reify classes flag to JRuby, every Ruby class that you define will be defined as a Java class or a JVM class. And so heap profiles, memory profiles, and all those tools will show Ruby objects right alongside the JVM objects, Scala objects, whatever that's running in the background. So you can get a full profile of memory. And of course, there's all sorts of command line profilers and all sorts of other little tools. Along with profiling, we've got monitoring. We've got an application that we have in production. We want to see what's going on. We want to be able to monitor the actual application performance, monitor if there's any problems. Again, we get JMX for free. There are gems that run on Ruby that allow you to define JMX entry points so that you can push monitoring information, push metrics up to a server. We have tools like JConsole and JVisualVM that can connect to an existing running application VM, JRuby VM, and give you all sorts of information about it. I'll show that in a moment. Most servers have additional tools on top of that, so depending on which way you deploy, Trinidad, Torquebox, or whatever you use, there are usually other metrics that are exposed as well to monitor the health of the application. And of course, New Relic and all the other application monitoring services have JVM support along with Ruby support. So you can get the full stack of monitoring just by using JRuby and hooking up to the existing tools you're used to. So Visual VM's the cool one that I wanted to show a little bit of. It does the basics like CPU, memory, and thread monitoring, showing you what's going on with the application. It can also do CPU and memory profiling of a running application, either by actually instrumenting the code and getting accurate counts, or by sampling and just kind of guessing where about in the code you are, what methods are being called a lot, what objects are being allocated a lot. It has another plugin called Visual GC that actually lets you see live over time what the different heaps in the JVM are doing. And you can see that they'll go up and they'll increase in size, they'll get collected, they'll increase in size, objects will get promoted to another generation. And heap analysis, doing memory dumps and seeing where the objects came from, why I have so many of these objects, and digging into the actual in-memory structure of your application, all built in, and this is a standard tool that comes with OpenJDK. So here is the first screen that you'd see. Basically shows the basics of what JVM we're running on, what the command line was, what the command line to JRuby was, some settings, additional JVM arguments and properties and whatnot. This is the basic monitoring pane, which has CPU information, shows you the overall heap size and the garbage, and you can see the memory occupation that's going up and down there.
And you can perform a GC just by hitting the button.
Yep, you can perform a GC and see if that solves some of your problems or reduce it down if you want to do a heap dump, for example. It's monitoring loaded JVM classes, monitoring the threads that are available. This particular run probably just had the 10 or so JVM built-in threads in the JRuby one. You can monitor what all the different threads are doing. The only Ruby thread here is main, which is the second from the bottom. You can see JRuby has one JIT thread that's running there. The JVM itself has a few threads for doing remote connections, for doing signal management, finalization, things like that. But you can see whether they're active, whether they're idle. You can see what they're blocked on. You can see if they're doing I/O or if they're waiting for a lock. All of that information will show up in here. This is the visual GC pane. So this is the standard parallel collector on the JVM, for which there's an Eden space where new objects are created, 2 survivor spaces where they're promoted as they get older, and then the old generation, where you expect objects to sit for a long time and be ignored, for the most part, by the garbage collector. But you can see all of the CPU information, you can see how much occupied it is, and if there's a leak, you'll see it steadily increase over time, and maybe it's old generation data, maybe you've got a problem in the young generation, maybe there's something, classes that are being loaded. All of that information is available here too. And then the final couple here, I mentioned that you could do heap dumps and analyze them. This is with that reify flag. So we can see normal Ruby objects here showing up alongside regular Java objects. I've filtered out the Java stuff, but we've got, this is actually a Rails application that was just booted, and most of the objects that are in memory are from Ruby gems at that point. Rails does a pretty good job of lazily standing up the rest of the system. But there are gems, there's about 180 gem specifications that have been created for this app. Looks like it might be running 2 instances of JRuby in this particular JVM. And you can just go right down the line and see all of the Ruby objects in memory, figure out where they're coming from, and maybe fix a problem if there's too many. Similarly, profiling. This is a CPU profile. It's a little bit cut off on the side, but we've got abstract controller, view paths, class method, something or other, set cookie headers in there. Now these kind of get sort of mangled names from JRuby, but they're still fairly readable. What we're hoping to do is possibly do a plugin that will unmangle all these as well. But the tooling is available, and you can profile a JRuby application with all the standard JVM stuff.
Well, there's FastHat.
Yeah, there's another project that's working on adding that sort of demangling, a little bit more Ruby-specific layer on top of these JVM tools. So more of that coming.
All right, well, up to this point, we've only actually talked about the JVM.
And it was thrilling, wasn't it?
Everyone loves talking about the JVM. The messaging's awesome. Wara, right once, run anywhere.
Yes, of course.
That still gives me nightmares. So one of the main features of JRuby is that you can actually script Java classes as if they are Ruby classes and work with them. So we're just going to port a few snippets of this Java FX clock application. Java FX is sort of like a pimped version of Swing. It has vector graphics. For this particular clock app, the dials go around, and if you dragged it larger, it would drag larger and wouldn't get jaggy. So there's 3 snippets here, and I'm really hoping that, oh, poop. Well, you can, there's an MH dot, and then, oh God, you can't see the set or the get. Okay, well, I'll describe this, because there's nothing we can really do about it. Especially since it's like 10 slides. At the top snippet, this is the code for actually drawing the minute hand. So we're creating a path, we're setting its fill to black, and then we have some relative drawing commands. If anyone's ever written PostScript, it's almost identical to PostScript. And so this is the code that knows how to draw a minute hand. In the middle, we define an event handler. This event handler is actually a Java interface, and we're implementing it as a Ruby class. The actual handle method is just calling this method called refresh, which updates all the hands on the clock, because it's the only part of the clock that moves. And at the bottom, we set up the timeline. On the first line, we say we want the timeline to go on forever. This is kind of the temporal part of the application. On the next part, we say once a second, send an event to the handler I provided, which we know will go and call refresh. And then we play it. So if we look at this code, and unfortunately I can see this better than you, that first line is set fill, and those next lines are gets. They're camel cased. It really does mostly look like Java at this point. It's kind of a mutant. But we provide a whole bunch of shortcuts to actually get rid of this artifact. The first thing we do is allow you to get rid of get on getters. So now instead of get elements, it's just elements. And we also do the same thing for setters. So now we can do fill equals black. And also camel case is really ugly in the Ruby space, unless it's a class name for some reason. But we can snake case it. So cycle counts, now cycle underscore count. Again, it's looking more and more like Ruby. We have a special feature that if the last argument to a method expects an interface, you can just pass a proc in, and that proc will say, okay, I'm that interface. So now we got rid of that entire class, and it's a little, well, how many characters is that? It's 10 characters. It's looking a lot more like Ruby now. Another thing that we do is we add common adornments to basic Java classes. mh.elements is actually an array list, or it's actually a Java util list. We alias add to be less than to make it behave more like array. We define an each method on it. We include enumerable into it. You'd have a hard time figuring out whether you were actually using a Ruby array or a Java array.
The thing that I really like about this example is that these are all, every single thing on here is a Java method call. It's calling into not Ruby code. But everything looks like Ruby code. It all feels like Ruby code. And it works pretty much like you'd expect. You actually can write Ruby code that calls into any of these libraries without any extra magic, and it still feels like Ruby.
So the truth of the matter is some Java APIs are much more amenable to just using shortcuts and looking okay. Many of them look like crap still because they're based off of Java idioms that just don't look nice in Ruby because we have things like closures. Here's a project that I wrote called Prugin. It allows you to make modifications to the Minecraft game. It's based on a Java API called Bucket.
And play Minecraft here? Some Minecrafters, yeah.
Do it.
You write plugins, you can script it in Ruby if you want.
But the idiomatic code in Bucket is pretty gross. It's really powerful and it's a really nice set of APIs, but doing it the Ruby way and doing it the Java way for this particular library, it's pretty stark. This spring I actually made a logo interpreter for Minecraft, and I just said, what the hell, let's show that instead.
That was a good choice.
Yeah. It's more centered, but the top's gone. Okay, well, what can you do?
Yeah, the important stuff's in the middle.
So this draws a pyramid. At the very top, we see this layer do. That's defining an action. After this is defined, whenever you go and specify layer, it just executes what's in it. If we actually look at that layer, we can see 4 times we go forward a certain amount, and then we turn 90 degrees. So if you visualize this, it's going to go and draw a square.
Everybody's done turtle logo at some point, right?
Has anyone not seen Logo? Or maybe they don't know what it is?
Okay.
Sweet. Yeah, this Logo really is a popular children's programming language.
Yeah.
Pivot's crazy. I added some more primitives for doing absolute directions. And I'm not going to walk through it, but it kind of goes up and positions you up to the next tier. And if we look at the bottom, we just kind of loop through several times. We draw a layer, we pivot up, and we draw another layer. Sweet. Oh, it's video time.
There we go. Now, Logo normally uses a turtle, but there are no turtles in Minecraft.
Yeah, there's a bug here. You can kind of see that that chicken's drawing it, but it's kind of stuck in it.
Yes.
It used to be on top of it. And then I forgot I installed this bouncing plugin, so.
But there you go. That Ruby code basically did all that. So if you want to write a Ruby script or a logo script that creates your entire farm, you certainly could do that.
And if we really want to tie this back to scripting, the point is there's some fairly Ruby gross Java code underneath this, and it took like 200 lines to make the logo interpreter, and that's probably only using about 50 or 100 lines of Ruby code on top of this complicated Java library. So it's very, very easy to do.
All right,
And
check it out. It's fun.
okay. Another goodie is Java native extensions. I hate all native extensions. I wish everyone only wrote in Ruby. If you replace shooting with write and penguins with C, this will make sense. You should always be asking yourself this question. If you can write it in Ruby and it's not like 100 or 1,000 times faster, screw that, just keep it in Ruby. If it's something you just can't do in Ruby, then maybe you can script it in Java if you're in JRuby, but then that's not compatible, so maybe you should use a late binding thing like FFI. Oh, but then that probably won't work on Windows, so you have to make some decisions. And if none of that works, then make a native extension. Just briefly, native extensions, again, this is this object homogeneity thing. By having it in Java, we can totally see it with our tools and understand what's going on. We're not just calling this opaque entry point into C and saying, what the hell happened?
Yeah, let's hope it works.
How much memory am I using?
Okay, so the last major section here, my favorite. Talk a little bit about the performance of JRuby today, and hopefully where we're going to be able to take it. Now we showed you this before. We could have just sat back and let the JVM get faster, and JRuby would have gotten faster right along with it. And this is cool. We're not going to do this, but it's cool that we get this all for free. But you look at where we are with Java 7 there and JRuby 103, and then we look and compare across Ruby implementations over time, or JRuby versions over time. And so there's our 103, which was faster than Ruby 1.8 on the far left, and then that massive improvement in the 1.1 series. Lots of incremental improvements along the way. So we've got the severe performance bottleneck. What is that all about? Why did we have that? Well, if we turn on some GC logging to see what's actually happening, we'll see tons of GC running for the version JRuby 103. A lot more than we would expect. In fact, there's even a full GC on there that actually has to clean the entire heap out. If we run with JRuby 1.7, we get one collection of about 7 milliseconds there, 10 milliseconds, 8 milliseconds, and obviously it's much faster. The JVM isn't wasting as much time, JRuby isn't wasting as much time. Now there's another outlier, another anomaly here. If we pull the 103 number off of there so we have a better graph, this is actually the JVM feature that's giving us this. This is Invoke Dynamic that's helping us do better. So taking a step back, performance-wise, so JRuby compiles Ruby down to JVM bytecode. JVM compiles that bytecode down to native code. And it's some of the best JIT technology in the world. It's been optimized for years to be able to optimize code to the fastest possible native execution, native instructions. And Invoke Dynamic makes it even better. So if we want to apply this to Ruby, let's look at how to optimize Ruby. First of all, we need to do less work. This is mentioned in Koichi's talk. It's mentioned in other implementers' talk. Do less work. Don't spend as much time setting up call frames. Reduce the overhead of doing dispatch, caching methods, avoiding hash hits and things like that. Reducing memory overhead internally. Try not to allocate as much memory. If you can optimize it at the VM level so that Ruby code doesn't optimize or create as many objects. And then once you've got that sort of thing, try to find more static patterns in the code. An application that runs long enough is going to be mostly static in how it behaves. And we can take advantage of that to optimize. If we look at what the JVM does, it's very similar. It's going to profile code, watch how it executes, and then optimize based on that what the hot paths are. Look for the hot paths through the code, the branches that are followed versus the branches that aren't, and make sure that the hot code is the fastest, most optimized code. And it does that by inlining code together. It does that by optimizing larger sections of code and inlining calls into one another. It does that through escape analysis, where it can eliminate a lot of transient objects And this is newer, but getting better with every release. So let's walk through a little contrived example here. We've got a little script that's going to loop a few times, call the invoker method, which calls foo. Foo creates an object. Now, what do we want to happen as far as optimizing this? Well, first of all, we want foo to inline into invoker. If that's the only foo that's ever being called there, it should essentially boil down to this code, right? Well, we're calling invoker inside the loop, so we want invoker to also inline and basically just have that object construction inside the loop. And now it turns out that we're constructing this object, but it's not doing anything. No one uses that object. That should be able to just go away, right? That's what we want the JVM to be able to optimize. Okay, so now we've got this loop that does no work other than incrementing I all the way up to 10,000. Well, this is the code that we actually should have at this point. The loop doesn't do anything, and it should optimize down to this. But then no one reads I either after this point, because the loop is gone. So this is what we want that code to optimize to. And this is what we can get with the JVM with Invoke Dynamic now. This is why it's such a big deal for us. So this is a Java 7 feature. It's getting better with each release. It's better in the Java 8 builds now too. It basically allows us to teach the JVM about Ruby and how it works. Dynamic calls can inline, constants become really constant, and all of these optimizations that you get for Java apply to Ruby too. So does it work? We released JRuby 1.7 with Invoke Dynamic support. So we'll go back to our little script. We've changed it a little bit. We took the object.new out to simplify it. We've got a loop to make sure we're running this code and letting it optimize. Some of the many flags for the JVM are print inlining, print compilation. Lets us see the JVM actually compiling the code that we've got. Lets us see how it inlines the code and what decisions it makes about how to optimize it. So we go back to our little progression here. This is the interesting part of the inlining output from the JVM. And since this is a little difficult to follow, we'll walk through it step by step here. So this block 0 at the bottom is basically that n times block, running a certain number of times in the JVM. And this is the base point from which the JVM is optimizing our stuff. We can see the less than operation, Ruby fix num op less than, and we see the is true for the loop that's being inlined as well, as it's hot. It's got to be in there. It's got to be optimized together. We can see the invoker call actually gets inlined like we expect it to. And then under the invoker call, we can see that the foo call also is getting inlined. And this is all going to be generated into the one native piece of code here. So there's foo. It's all pulling that code in. And then finally, the last operation inside this block is doing the increment of I. And this is also getting inlined. Everything here inlines and becomes one piece of native code that's sent to this processor. And it can see a lot of these optimizations, more and more of them, as they make Invoke Dynamic optimize better and better. So now does it actually help? We're inlining stuff, we're doing what we think we should be doing, but do we get the performance we want? Well, we're hearing from more and more people that JRuby 1.7 is definitely faster. Even without Invoke Dynamic, it's faster. But Invoke Dynamic just makes it far and away the fastest we've got right now. So let's see. Here are a bunch of benchmarks. Base 64 is just a base 64 encoding. Richards is kind of a VM simulator. It's things that are difficult for VMs to do, like polymorphic dispatch. Neural is a little CS101 neural network. Mandelbrot is just going to generate a Mandelbrot, fractal in memory. And then red-black is just a red-black tree. It creates the big tree, walks it, deletes elements, and so on. So this is JRuby on Java 6 without Invoke Dynamic. And we're pretty good. You know, this is compared to Ruby 1.9.3 and faster in most cases for these particular benchmarks. And if we add in Invoke Dynamic, just with what we've done today, just with what we got in JRuby 1.7, and we're multiple times faster. On some scripts, 5 to 10 times faster, without doing anything other than using a newer JVM and turning Invoke Dynamic on. Smooth Sort was one that came up recently. Chuck Remus implemented a port of a C++ version of Dijkstra's Smooth Sort. And so we looked at it, and we did some minor changes in JRuby, tried to optimize to make sure it runs fast. I threw Ruby 2.0, and this is built today. So this should have at least all of the optimizations that are in Ruby trunk today. And again, it's significantly faster in the JRuby case. All right, so what about Rails? That's the big one that everyone cares about. And we're running close on time here. So here's one testimonial that it runs Rails a lot faster than 1.9.3. Here's some of the TorqueBox guys. They've done some measurements where they show latency is lower, throughput is better, Other metrics like CPU usage, you're using less CPU time, you've got more free memory. This stuff actually does work. All right, so wrapping up, it's your turn. We want you to try your apps on JRuby, try your libraries in JRuby. If you're not testing your library on Travis, you should be. And if you're not testing it on all the implementations, you should be. So please turn on JRuby, turn on Rubinius, turn on whatever other implementations you can get access to. Let us know what you think and help us improve JRuby. If there's edge cases that we don't support or if there's problems, tell us and we want to fix them. We want to work with you. And is anybody interested in a BOF this evening? That'll just like questions and answers and office hours kind of stuff? All right, there's a few folks. So we'll hang out in room C, I guess is equivalent to track 3. It's the far end of like 405, 406 rooms, whatever. We'll be in there around 6:30 and just hang out until 7:30 or until we feel like we're done. All right, and the last few plugs, there is a Using JRuby book. We're going to be updating this, but it's still an excellent book right now for getting into JRuby and getting the details of it. Deploying with JRuby, if you want to take the next step and put an application in production, excellent book, covers a lot of different ways of deploying applications. And that's all we have. And I don't think we have time for questions. If you want to grab us in the hall or come to the BOF, we'll be here all week. So thanks very much.